This image shows a model of the Earth's crust. When tectonic plates collide with each other, they exert enormous pressure on each other. So this is several layers of sand in a box with plexiglass sides that you can see through. And then there's a plunger that's pushing from the right to the left. So there is a force being applied on this representation of the Earth's crust built up from layers of sand. Think about all the other forces that are acting here. If there's an applied force of the plunger on the sand, then there must be a normal force pushing back against the surface. There's also gravity and the normal force pushing up against gravity. And then there are the forces of the different layers pushing against each other. This is how mountains are formed. Rather, this is one way that mountains are formed. This shows that the Earth is not as stable as it seems to be. When we think of rock or ground or mountains, we tend to think of them as stable and unchanging, but they're not. They're just changing much more slowly than we usually perceive. This kind of dynamic or changing structure would be unacceptable in an engineered structure like a building or a bridge. An engineered structure must be stable. That doesn't always mean it doesn't move at all, but that means that it can resist the forces that are the external forces that are applied to it. A building, for example, may bend and sway in the wind. A bridge may flex under the force of the cars that drive over it, but they return to some kind of equilibrium state, some kind of stable state. This has to be engineered into the design. So when engineers talk about the different forces that are the different external forces that are applied to their structures, they call those forces loads. A structure must be able to resist load. So if the weight of a car is expected to push down on a bridge, for example, the bridge has to have the ability to push back up, to exert a force back up in the opposite direction. Otherwise, you'll have unbalanced forces and the bridge will accelerate downward. And accelerating downward is not something that's usually desirable in a bridge. The application of loads to a structure can cause internal forces, where the particles that make up that structure push against each other, and they create internal forces called stresses. So these are both terms that have to do with force. Load is an external force applied to a structure. It could be a force that's caused by weight that's applied to that structure. It could be wind. It could be anything that is expected to be applied to that structure. And the stress is the force that is experienced within the structure, within the internal forces where the particles push or pull against each other. Designers have to think of all the internal stresses that might occur in their structures that they design. For example, If an architect or an engineer is going to design or build a house, they're going to have to consider all the different loads that apply force to that house. This house, even though it's not very common in Southern California, this house has a basement. So part of it is under the ground. If you think about all the loads that a house experiences, it experiences the force of wind. In some areas, this can be very high, like in places that are prone to hurricanes. In other places, or even sometimes in the same places, houses may need to be built to withstand the force of a load of snow on the roof, or rain on the roof, or even just wind blowing and hitting the roof. A house that has a basement like this, or even a footing is just a part of the house that goes under the ground. And even though our houses don't usually have basements in this area, think about all the buildings that have parking garages that are under the ground. All of the weight of this ground pushes against the walls of the basement or of the subterranean structure. And if the ground absorbs a lot of water, that's going to increase that amount of force that's pushing against the walls down there. So an engineer or an architect has to consider all of these different stresses caused by all of these different loads. Not only that, the weight of the roof gets transferred down to the walls. The walls have to support the roof. This is what a load-bearing wall is. You might have heard that phrase. A load-bearing wall is a wall that is supporting the roof. Sometimes walls have extensions up in the attic that help support the roof, and sometimes the walls are just there to separate the rooms. So some walls are load-bearing and some walls are not. So the roof exerts a force down on the walls, and then the walls, or the weight of the entire house, exerts a downward force on the foundation. And the foundation, this is why you may hear, it's kind of a cliche, that if for a house to be strong or a building to be strong, the foundation must be strong. And that's true. The foundation supports all of those weights pushing down because of the presence of that house. So foundations are often, they could be big slabs of concrete, or they could be concrete posts sort of that are buried down in the ground, and the house will be built on those posts. But the foundation is what gives the house its strength and its stability. Its ability to resist all of those downward forces that are transferred through the structure of the house, through the roof, through the walls, through the floor, down into the foundation. At the beginning of this lecture, I mentioned that the Earth is not as stable as we think, that it's changing, and we looked at some of the forces, or one of the forces that helps build mountains. Well, once a mountain is built, its weight presses down on the crust of the Earth. And so that force, that downward force, the weight of the mountain, must be countered by an upward force, a normal force, if you will, of the crust pushing back up on the mountain. Now, over time, those mountains push down and they sink into the layer just below the crust called the asthenosphere, and the mountains themselves become lower. They actually sink. However, over time, those mountains also wear down. They get smaller, not just because they're sinking, but because their surface is actually wearing away from all the wind and the rain over thousands or millions of years. And so that mountain actually becomes lighter. The material of the mountain is worn away over time. That's called erosion. Erosion. So the wearing away of the land is called erosion. And now there's less of a force pushing down. And so what happens is the crust can still push back with the same amount of force, but so now the upward force is greater than the downward force of the mountain. The mountain actually tends to rise a little bit. There's a net upward force on the mountain, so it floats higher until the forces are again balanced. So it's a temporary floating until those forces become balanced again. Forces act in pairs, and when forces act on an object, they create stress in that object. So we have different ways of describing those stresses. If you have an object and the forces that are acting on it are pushing in on from opposite directions, then that's a stress that we call compression. Sometimes the forces that act on an object are not pushing in on from opposite sides. Sometimes they are pulling, it's like they're trying to pull the material apart. That is a stress that we call tension. We've already talked about tension force when we talk about pulling something with a rope or a chain. Well, tension is also a type of stress. Now, sometimes those forces are not aligned to each other, and they might not push the internal forces might not be acting directly against each other, or they might not be acting directly against each other. They might be aligned or misaligned, so that they're actually causing. So here we see that in compression, these particles that are in here are being pushed closer together, or they're having a force pushing them closer together. Here in tension, those particles have a force that's trying to pull them farther apart. Well, what's happening here? Here you have a force pushing this way and a force pushing this way. It's these particles in between that are going to be affected. They're being kind of, that's where you might expect to see something break. And so this is called shear stress. So we have three types of stress that we talk about. We talk about compression, tension, and shear stress. Sometimes we can see the effects of these stresses in rocks, and you can see them on an everyday basis. If you are in a place where the rock surface is newly cut, it's not covered with plants or anything. Quite often when rock forms, it forms as a sedimentary rock. So one type of rock is sedimentary rock. Sedimentary rock is rock that forms when sediments are deposited usually by a body of water, like maybe at a river. Okay, so sediment is just the small pieces of dirt and rock that are carried. Maybe they're carried down a river and then they settle at the bottom of the river and they form layers. And because of gravity, they're going to form horizontal layers. So sedimentary rock forms in horizontal layers. Now, sometimes after that rock is formed, so it takes a long time for sedimentary rock to form. There are layers, but then it takes a lot of pressure to turn those tiny little pieces into actual rock. This picture, this image, shows what used to be, well, what still is sedimentary rock, but it used to be in horizontal layers. And it had many forces and stresses applied to it. So you can see those layers that used to be horizontal and aligned in the same direction as each other, those actual layers have been folded and bent. And this is one feature that we can see in rocks. If you've ever seen images of the Grand Canyon, you can very clearly see those layers of sedimentary rock. And throughout the canyon, you can see areas where geologic forces have caused enough stress and have put enough load on that rock to actually cause it to bend or to fold over time. There are three types. So this image represents tectonic plates. The Earth is covered with a crust. Underneath the crust, there's a semi-fluid substance called the mantle. So the crust, this brown area so this is the crust right here. The crust is here. And then down here, this is the mantle. This is the top part of the mantle, or the boundary between the mantle and the crust is called the asthenosphere. The mantle is very hot. It's molten rock. So the crust is broken into tectonic plates, these gigantic plates that are floating on the mantle. And since they're floating, they move because the Earth spins around. There's a lot of stuff happening. It's partly the Earth spinning that causes the plates to move. Also, the mantle, since it's fluid or semi-fluid, there are currents that occur inside it from the heat coming up and then moving the plates around. These are called convection currents. But there are three types. So there are three types of plate boundaries that we discuss. One is called the convergent boundary. The convergent boundary is where two plates come together. And where two plates come together, they don't just crash into each other. They push against each other, but then one of them, whichever one is heavier, is going to be pushed down under the other one. Okay, so this one, the oceanic plate, is heavier than the continental plate on the right. The oceanic plate is pushed down under the continental plate, and then as it sinks down into the mantle, it heats up and it becomes part of the mantle. The continental plate then moves up on top of the oceanic plate, and so that's how mountain ranges form. A good example of this is the Himalaya Mountains, in the border between the Indian plate and the Eurasian plate, where the mountains are being pushed up. This is also a place of great volcanic activity, where the magma from the mantle comes up through breaks in the crust. So that is a convergent boundary. A convergent boundary is where the two plates are coming together. That's an area where compression occurs. Compression occurs there. The second type of boundary is called a divergent boundary, and just like it sounds, that's where the plates are diverging. They're moving apart from each other. So this plate is moving away from this plate. And where that happens, the plates are pulling apart, and so the magma, the mantle, pours up through the gap that's formed between them, between those two plates that are coming apart. And so you get a whole bunch of little volcanoes and volcanic vents along a divergent boundary. And of course, you get earthquakes too, where you have volcanoes. Most divergent boundaries happen in the ocean. There is at least one that is in East Africa, which is on a continent, and that's called a rift. It creates a rift valley where the plates pull apart and the land kind of falls down into the gap a little bit, creating a great valley. The third type of boundary is called a transform boundary, and that's where the plates would move. They would move anti-parallel to each other. So if one is moving north, the other one is moving south. They slide past each other. So convergent, they come together, that's compression. Divergent, they pull apart, that's tension. And then the transform boundary, they move past each other, but they don't move past each other smoothly. So when they move past each other, they create a lot of frequent earthquakes. And that's what's happening in our area, where that's why we have a lot of earthquakes in California, because we're near a transform plate boundary. I mentioned the term stress a number of times. Well, stress is an actual numerical value that we can calculate. So it is, if we're going to engineer materials to resist stress, we need to have some way to measure that amount of stress and to design materials and structures that will stand up to those stresses. So stress is a value that, stress is equal to force divided by area. So you can kind of, so a force applied over a small area creates more stress than a force applied over a large area. Once again, stress, which is represented by this Greek letter, I believe it's sigma, is equal to force over area. So a greater force is going to create more stress. A greater area, so if that force is applied over a greater area, it's going to decrease the amount of stress. If you push something with your palm, that's a greater area than if you push somebody with your palm, then that's a greater area than if you poke them with your finger. So if you poke somebody with your finger, they're going to feel that stress more so than if you push them with your palm with the same amount of force. Different materials can withstand different amounts and different types of stress. So some materials are strong under compression, some materials are strong under tension. So it is really important to understand stress when you are selecting materials for a design. This slide challenges you to analyze the forces in a uniform, as a group of uniform horizontal rock layers. Let's look at another structure where we can think about how different stresses can act on the same structure. So if I have a very simple bridge going across just a ravine, a valley or something, there are going to be, and then let's say a car drives over this bridge. The car applies a force downward. And I'm not sure what's happening with my drawing tablet, but imagine that that line's not disappearing. Okay, so a car exerts a force down on that bridge. Think about how we can experience both tension and compression here. If the bridge bowed down like this, there's an exaggeration. So that's what's happening. It's just not happening on quite as large a scale on the bridge. If it bows down to make sort of a smile shape, what's going to happen is the particles on the bottom there are going to be pulled apart. So these are going to be pulled apart on the bottom part of the bridge, and so they're going to be under tension. And meanwhile, the bridges on the particles on the top are going to be pushed together. They're going to be under compression. So those internal stresses can actually work against each other. So when somebody is designing something like a bridge, they need to design structures that can withstand those forces of compression and tension. And one way to do that is with something called a truss. You may have seen bridges like this where there are triangular members, and these are at very specific angles. And so these members, some of them are while some of them are under compression, others will be under tension. And so the forces are balanced out throughout the bridge. Many of the bridges that we see, like if you look at a freeway bridge, it's probably quite often it's going to be a truss bridge. It's going to have these triangular structures inside it. They're just covered up by concrete. So it'll have some kind of a skin on the outside, so we don't see these trusses, but they're in there. That's what gives things strength. It's a bridge is not just a big slab of concrete. Okay, that would not be very strong actually. Within that bridge, whether it's a footbridge or if it's of any significant size, if it's a footbridge or vehicular bridge, it's going to have some kind of internal structure, usually made of steel girders that create a truss inside them. And there are other kinds of bridges. There are bridges that resist stresses by having cables hold them up. Okay, these are called suspension bridges or cable stayed bridges. And there are different structures that can be done to resist stresses. Trusses are a very common one. It's spelled like this. But there are other techniques that engineers employ as well, including structural techniques and materials, using the correct materials.